Hello, welcome to Penny for My Thoughts Lab. Before we begin, let's just have a look at the setup here. I have two weights hanging by threads across a pulley at the top. Let's just look at some basic ideas. First off, you ever wondered how an elevator works? Well, this is an elevator. You always use a counterweight because it's much easier to move the elevator if it's balanced like this. Speaking of balance, can you see Newton's first law in here? An object at rest remains at rest unless an unbalanced force acts. Well, they're at rest, so there must be no unbalanced force. That means the weight going down is equal to the tension going up. The weight going down is equal to the tension going up. Notice even when it's moving, it still has no unbalanced forces because it moves at constant velocity. Another thing you might want to go back to think about is, I said that for the bottom weight, the tension's going up. And for this weight, the tension's also going up. The pulley just bends the string, but the two tensions are in opposite directions. That can be confusing. Well, think of a simple string here, guys. I got a string. I'm pulling outward on it. So my thumbs represent my pull from my hands. And yet the string's not moving. So if my left thumb is pulling to the left, that means the string must be pulling with an equal amount to the right. Same thing on the other side. My right thumb is pulling to the right, so the tension on the string must be equal and opposite. So the two tensions are actually in opposite directions, just like they were when we bent it a minute ago in the lab. Over here, the tension on both strings is up, and it's equal. Okay, now let's have a look at the lab. What I'm going to do is I'm going to change one of the masses. The weights that were hanging were 100-gram weights, so now I'm reducing it. Now there's 80 grams of weight on one and 100 on the other. Do you think it's still balanced? No. See, now it accelerates. But the tension in the string is still the same everywhere. So the first thing we're going to do is measure the acceleration. You should be able to derive, using Newton's laws, a formula for the acceleration given the two values of the masses. So we will measure using our usual setup that gives us acceleration from the computer. So your data sets will have acceleration that comes from the computer. Now when you try that, you'll get various runs, so we average out. When you analyze the acceleration that this machine gets, you'll find out it's not quite what Newton anticipated. Or this machine gives good repeatable data, but it's not calibrated. It's not accurate. So what you're going to do in this lab is two things. We're going to take a penny, a little piece of blue tape. The weight or mass of the blue tape is not a source of error in this lab. It is very small. And we're going to tape a penny onto the lighter mass. And we're going to again run the computer to measure the acceleration. Notice it's slower this time. That should make sense to you. We'll collect a few pieces of information this way, a few pieces of acceleration. So now, your job in this lab is first just using Newton's laws as you calculate them, determine the mass of the penny given the measured acceleration. Now the second part of this lab is for you to make a scale factor. When we ran with the known masses, which are given to you in your data set, the calculated acceleration doesn't match the experimental acceleration. But you can make a scale factor that will correct the measured acceleration to give you the Newton or theoretical acceleration. A multiplicative scale factor. You could multiply the measured acceleration to get the experimental acceleration. So you're going to first find the mass of the penny in the straightforward method using Newton's laws, and then the second time apply the scale factor. The scale factor will correct or calibrate the experimental acceleration and should give you a much better result.